Hello friends and students. Today we are going to use partial decomposition method for integrating rational functions. So what is partial decomposition of rational functions? If you guys don't know or are not sure what a rational function is, then I should clarify it here once again. So this is a rational function if both the denominator and the numerator, both of them are polynomials of x, then this is called a rational function. Suppose we are given this function, then we can write it or rather decompose it into two functions just by dividing it and taking the remainder. Now I have just moved it to the left hand side of the screen to make space for completing the division here. So this is our division. So 1 is our first estimate, because dividing x square and x square we get 1. So 1 is our first estimate. Now if we just complete the division here, multiplying 1 with all these three terms, and we are going to write each of them under the dividend here. Now changing their signs, we get this. So we are left with only negative x. This is our remainder. So we may write this as 1 minus x divided by, in this process. So this is how we can separate it into two different fractions. So using these types of methods, and I agree not all of the problems are going to be solved using this same division method. There are different tricks and tips. We are going to discuss them throughout the video. So keep watching and watch till the end of the video if possible, without skipping any portion. So this is our first problem. In this case we are observing that px, or the numerator polynomial, is right now a higher degree polynomial than the one at the denominator. Here the degree is 2 and here the degree is 1. So this is a linear polynomial and this is a quadratic polynomial. We can see that. So if that is the case, then we can simply divide the numerator by the denominator and proceed with the method shown in the previous problem, where we could just decompose the rational function into 2 or 3, depending on the cases that we have, 2 or 3 different simple fractions, which are very easy to integrate. So using division, we may complete the division here. So first estimate is x. So just changing the signs, we have this one cancels out, and this here is, if I am not mistaken, then this is the remainder for this stage. Now we proceed again with an estimate of 5. I think yes, 5. So we get 5x minus 10. So now we are left with just 15 as remainder, and this one is the quotient. So we can write this as x plus 5 plus 15 divided by x minus 2. Now this is going to be integrated with respect to x. So it becomes very easy. We simply distribute the integration operator into 3 separate terms. So we distribute it across the 3 separate terms. This one is one term, this one is second term, this one is the other term. So we are left with 3 different integration problems. So this is the first one, is very easy. It is going to be, we are going to use this method, integration of x when n is not equal to minus 1. We can write it as when n is not equal to minus 1. So this is what we are going to use here. So if there is nothing, then that means there is 1. So it is going to be this one, and this is nothing but only x, because if we differentiate x with respect to x, we are going to get 1, and there is nothing, that means there is 1. So x, and this one is a little bit indirect, but suppose we assume that x minus 2 is z, then how does this integration transform? This integration transforms to this. So what is that actually? Log of modulus of z, and z is what? X minus 2. So I'm going to skip that part and directly write the answer here. So this c is our integral constant. This one is a little bit more difficult because the denominator at the polynomial at the denominator has a degree of 3, and the polynomial at the numerator is a linear polynomial, so it has a degree of 1. So we cannot simply proceed with the division, and we can do is factorize the polynomial at the denominator completely into 3 linear polynomials if possible, taking x common, and we can easily factorize this quadratic polynomial using any number of methods at our disposal. So I'm going to use the middle term factorization. I'm going to use middle term splitting factorization. I hope you guys are all familiar with that simple process. So this is what we are left with here. So for the shortage of space, I am going to write it here. Remember this. And now we are proceeding with the actual integration. Now I can write this as this because the polynomial at the denominator has a degree of 3, so it has 3 degrees of freedom. So I am going to use 3 unknown quantities a, b and c. Hope I am clear. After multiplying both sides with the denominator of the left hand side, we get, and remember that this is an identity, okay? So whatever value I put for x on both sides should satisfy the relation because this is an identity. So I am going to take convenient values or suitable values of x to put on the left hand side and the right hand side. First, if I take a value of 0, it gives us minus 1 in the LHS, and it gives negative 2a on the RHS, and these two terms cancel out. So a is actually 1 over 2. Similarly, proceeding in the same manner as shown before, if I place x is equal to minus 1 on both sides, on the left hand side we are left with minus 4, and this term cancels out, this term cancels out. On the right hand side we are left with 3b. From this equation we get that value of b is negative 4 over 3. Similarly, putting x is equal to 2, we are left with 5 on the left hand side, and these two terms cancel out, and here we have, I think, 6c. So c is what? C is 5 over 6. So our integrand has been decomposed into 3 fractions, simple fractions which are very easy to integrate using this formula. Let me write it here. So suppose this is the actual variable, so the antiderivative of this 1 by t is log of mod t plus some constant. This is not important, but this is the actual antiderivative that we are going to work with a lot actually in this video. Now the rest is easy for this problem. I equals integration of 1 over 2 is a constant, so it comes out of the integrand. This negative 4 by 3 is also a constant, and 5 over 6 is another constant. So simply assuming that x plus 1 is equal to z or x minus 2 is equal to z, we can easily find the antiderivatives of these functions. So if you are finding it hard to understand, just use method of substitution for these two integral problems separately. I made space for writing the integral constant here. So this is the integral constant. So we are going to move to our third problem. This is our third problem. Here also the degree of px is equal to degree of qx being the polynomial at the denominator and px being the polynomial at the numerator. So the degrees are the same. So we can simply proceed with division. So 1 is going to be our question. This is going to be cancelled out. And this becomes this. So this is our remainder. So we will write our original integral as, now this one is going to just give us x for the integration, but what about this part? Now we just have to factorize this denominator. X square minus 4 is using this formula, a square minus b square equals to a plus b into a minus b, which I hope that you have studied in 7th standard or 8th standard. It's fairly uncomplicated and easy to understand how this comes about. So we are going to use that. Because here what is 4? 4 is 2 squared. So this is how we get this. Now 3x plus 5 divided by so the numerator is this and the denominator is this. Now let us write this as this. I'm going to erase all that. Now if you just multiply both sides by a denominator of the left hand side, we are left with this relation. This is actually an identity, because we have assumed that suppose this is expressible as the summation of two different fractions. So this is an identity. Now if you put x is equal to -2, then we have on the right hand side we have -4a and this is -1. So what is a? A is nothing but 1/4. The coefficient of b is 0, so b cancels out. Now similarly, if x is 2, then a cancels out, and on the right hand side we have 4b, and on the left hand side we have I think 11. Therefore b is 11/4. So our original function reduces to 1/4 x plus 2 plus 11/4 x minus 2. So similarly, this one is going to give us x, like I said earlier, and this is a constant, so this is going to come out, and simply we are going to have this, and then 11/4 is also a constant, and we are going to have, now there is no more space to write the integral constant. I'm going to write this below like this. I hope this is clear. Now for these types of problems, we are going to use logs and the integration of log functions a lot. Now suppose this is the next problem and there is a repeated root here. Now what are we going to do about this? So the division is not possible because the degree of the numerator polynomial is less than the degree of the denominator. The degree of the denominator polynomial is 3 and that of the numerator polynomial is 1. So we cannot proceed with the division. What we have to do is use this. If there are any repeated factors in the denominator, remember this. Suppose here we may write this, the first factor is x plus 1, we may write this like this, but we have to write not only 1 for the 2x minus 1 which is a factor, but also another term dedicated for the highest degree of the factor. Here the highest degree is 2. Suppose there were 3 repeated factors in the denominator, then we would have had to write 4 terms. One for the same, the first term would have been the same because this factor is the same. Then one for this first degree, then another one for the second degree of the repeated factor, and the last one for the final degree, the third degree for the repeated factor. This is how we would have had to write the identity for proceeding with the separation of terms. That means the decomposition of fractions. Anyways, if we multiply both sides by the denominator of the left hand side, we are left with x minus 2 equals a into this plus b into 2x minus 1 into x plus 1 and c into just x plus 1. I hope this much is clear. Now proceeding with in the same fashion that we have done in the past few problems, we are going to put suitable values for x for the left hand side as well as the right hand side, so as to cancel out the different terms as the case may be. So in this case we are going to assume that x is minus 1 first. So if we assume that x equals to minus 1, then what do you get? Since there are repeated factors, it cancels out. So if x is minus 1, then left hand side is minus 3, and therefore a is minus 1 by 3. So a is minus 1 by 3 or negative 1 by 3. Now if x is 1 by 2 or 1 over 2, then this first term cancels out because the coefficient of a and b both become zeros, and we have here is negative, I think, 3 by 2. So c becomes negative 1. It is pretty self-evident. I think I don't need to explain this any further. So c is negative 1. Yeah, let me write it like this. C is negative 1. Now suppose x is 1. Now what we have on the left hand side is negative 1, and this is actually a plus 2b plus 2c, I think. So negative 2b equals to 1 plus a plus 2c. But we know the values of 1, a and c. So what is a? A is negative 1 by 3. Negative 1 over 3, and c is negative 1. So this is actually negative 2. This is actually negative 2. So if we simplify the right hand side, we get b is equal to 2 by 3. So I think you can guess that for these types of problems, the partial decomposition is the main challenge. After that, the problems are very easy to solve. So now I becomes equal to negative 1 by 3 dx over x plus 1 plus 2 by 3 dx over 2x minus 1 and negative of dx whole squared. Now let me do a small substitution to make it easier for you to understand. So we are assuming that 2x minus 1 equals to z. That means 2 dx equals to dz, or I could have written it in this form: dx is equal to dz by 2. Now what I becomes here? I becomes this. I'm not going to change the first term because it is not needed, but for the second and third terms I'm going to use the z as a substitution for this function. Now what we are left with is dz by 2. So I'm going to multiply 1 by 2 with the constants here, and this is z negative of dz, and again 1 by 2, and this is z squared. Therefore the process is fairly straightforward. This is just a matter of writing down each of the integrations. This is our integral constant, and if you are wondering how this is coming like this, we are using the integration of x to the power in this formula, where n in this case is minus 2. So x to the power minus 2 plus 1, it gives us x to the power negative 1, and this becomes negative 1. So negative negative, they cancel each other out, and we are left with a positive sign, and this is just z to the power negative 1. But what was z? Z was this was z, so I am going to replace z with the x. So I am replacing z with the original function of x. So this is our integration. I hope it was clear, and now we are moving to the fifth problem. That will be the final problem. Now we have this unique looking problem. I am saying this is unique because the denominator doesn't completely factor out into simple factors of linear functions. The denominator becomes the multiple of, or the product of, a linear function and the quadratic unfactorizable function. And we are staying away from complex factorizations right now. We are simply in the domain of real numbers and real fractions. So let us solve this problem using only real numbers. So what is going to be my assumption for the right hand side? Now this first one is easy, a divided by the simple linear function. This one is quite easy. Now for the second fraction, we are going to write the denominator, which is also easy, which is also very straightforward, but the numerator is the tricky part. So on the numerator we are going to write bx plus c. Why bx plus c? Because for the denominator we have 3 degrees of freedom. So we need to take 3 unknown constants. Yeah, but here we are getting only one constant, a, because the denominator is having only linear polynomial. But in this case the denominator is a quadratic polynomial, so there is an option for us to take bx plus c. Am I clear? Because this one is quadratic, so we may use here a linear polynomial, a linear combination of x's and constants. So this one is an x term, and this one is a constant term. Suppose this was an unfactorizable cubic polynomial, then we would have written it like this. Suppose this was cube, and this was assuming that this is unfactorizable, we would have written this like this. Am I clear now? I hope I am clear. If I am not clear, then you may write in the comments what you don't understand about this. I will try to explain there. Again, multiplying both sides with the denominator of the left hand side, we get x is equal to, this is our identity. Now assuming x equals to 1, we have a is equal to 1 by 3. It is pretty self-evident and pretty easy to understand. Just put 1 in place of x. Wherever there is x, just put 1. So this one becomes 1 square plus 1 plus 1. So 3a. This cancels out because 1 minus 1 gives us 0. and this is 1. So A is 1 over 3. It is pretty easy to understand. Now suppose x is negative 1. So the left hand side gives us this, and we have here is A, and this is C minus B into negative 2. So this is actually this. If you replace the value of A with 1 by 3, we get it becomes an equation like this: B minus C equals to, I think, negative 2 over 3, because we divide both sides by 2 then. But this relation does not give us any value for B or C. So we are going to take another value of x. Hopefully that will give us a value easier than this, or an equation that is easier than this to solve. So if we put x equals to 0, what do we have? We would get this. If x equals to 0, then C is just equals to A. C just equals A. Now if C equals A and B minus C is equal to negative 2 over 3, then what is B? B is equal to 3 minus 2 by 3, which is, I think, negative 1 over 3. I can see that I am pretty bad at using the screen space. So this is what we have. Then our I becomes, I'm going to quickly write this down. It has been decomposed into two different fractions. This is fairly easy to integrate, but this one is still creating some problems for us. So what can we do now for this one? So let us assume, let me use a different color for this. Let us assume that x square plus x plus 1 is equal to z. Then what happens is 2x plus 1 into dx equals to dz. But there is not 2x plus 1 here. So let me manipulate this in such a way that there is a 2x plus 1 beside dx here. I can do that by simply multiplying 2 here and 2 on the inside in the numerator. So it is going to give us 2x minus 2, and if I add 1, subtract 1, then it will give us this. Now it is simply a matter of just replacing the value of x square plus x plus 1 with z, and then on the third term just completing the square on the denominator. This is all I'm doing. So if I complete the square on the denominator here, it is going to be looking like this. Okay, this is fairly easy to understand why this is coming, because this is z, and I have simply completed the square on the denominator on the right hand side here for the third term. This is going to be this. Now I am going to erase the first two lines of the problem for the shortage of space. So what will be our final answer? The final answer will be something like this. Now what is this? This looks a lot similar to something we know. This. What is the value of this? We know the value of this to be, for those who are not familiar with this type of notation, this is nothing but arctan. So the answer is going to be 1 over root 3 by 2. That means it is going to be reciprocal of this, and arctan So if I multiply 2 on the both the numerator and the denominator, we have, and this becomes 1 over root over 3. And let me write the original function in place of x, so that it will give us the final answer, which is something like this, where c is the integral constant. This video was a fairly lengthy video, I am not going to deny this, but you have to carefully watch each part of this and repeat it. If you find something difficult to understand, share your comments with me. Share your comments and feedbacks with me so that I may improve in the future. Thank you for watching.